Hey everyone, and welcome back to this class, Unsupervised Deep Learning, Part 2. In this lecture, we are going to discuss some of the background behind the variational autoencoder. The variational autoencoder is a neural network that can both learn to reproduce its input, but also map training data to a latent space and then draw samples from the data distribution by sampling from the latent space. If that sounds complicated, don't worry, as we will be going through that process in much more detail throughout the next few lectures. First, let's discuss the name a little bit. Variational autoencoder. If you've been following my courses, then you probably recognize one of these terms, but not the other. So let's discuss the easy one first. We know what an autoencoder is. In fact, we practice building one as a warm-up to this course. An autoencoder is just a neural network that learns to reproduce its input. One important feature of autoencoders is that typically, we choose the number of hidden units to be smaller than the input dimensionality. This creates a bottleneck and forces the neural network to learn a more compact representation of the data. So what do we mean by that? Well, suppose we can teach this autoencoder to faithfully reproduce its input. Let's assume that the input size to this autoencoder is 784 dimensions, and the hidden layer size is 200 dimensions. That means we have learned to represent whatever image we've passed in, which consists of 784 numbers, as a much smaller code instead, 200 numbers. Well, what does this mean? That means out of the original 784 numbers, many of them were redundant. The true amount of information contained in the original data must then be much less than 784. We typically call these 200 numbers in the hidden layer the latent variable representation, and we typically use the letter Z to represent it. This shouldn't come as a surprise, since we've consistently used the letter Z to represent the hidden layers of the neural network and latent variables in the past. We'll touch on this concept again later. The other term in variational autoencoder, which you probably haven't heard of, is variational. This refers to variational inference or variational Bayes. These techniques fall into the realm of Bayesian machine learning, which you'd have to have taken a difficult graduate course in machine learning to learn about. One way to think of variational inference is that it's an extension of the expectation maximization, or EM algorithm. Just a warning, a lot of this information is not directly related to how variational autoencoders work. It's just sort of historical information to give you a better sense of the big picture. So if you don't quite get it, don't worry. It's not required to understand the underlying mechanics of the variational autoencoder. As you may recall, the expectation maximization algorithm is used when we have a latent variable model and we can't maximize p of x directly. An example of this is the Gaussian mixture model, which we've seen already. The expectation maximization algorithm gives us a point estimate of the parameters. In other words, it can be seen as a frequentist statistical method. What variational inference does is it extends this idea to the Bayesian realm, where instead of learning point estimates of the parameters, we learn their distributions instead. So does this mean you have to understand variational inference in order to understand this course? Luckily, no. You must be happy to hear that there is finally one topic that is not a prerequisite to this course. So why don't we need to understand variational inference in order to understand variational autoencoders? Well, it would certainly help to have a deeper understanding of variational autoencoders, but learning how one works mechanically and implementing one in code do not require this deep understanding. And as I mentioned earlier, if you do decide one day that you want to learn about variational inference and similar Bayesian methods, realize that it will be extremely challenging, very difficult conceptually and mathematically. so it wouldn't be practical to make it a prerequisite to this course. So that's just some background on what elements combine to give us variational autoencoders. It takes one thing we know about, autoencoders, and one thing we probably don't know anything about, variational inference, and combines them together. In the next few lectures, we'll look at the mechanics of training and sampling from a variational autoencoder and an implementation in code.